Come on in, everyone. Just waiting for everybody to show up. I'm also in the process of fixing those two tests that were in the wrong category. I did that in one class. I'm not sure if this class is having the same problem, so hopefully the thing will run fast enough where I can actually see it. Let's see, I got test 1, 2, 3. Nope, 4, and well, 5 is there, but test 4 is not. Let's see, test 4. Where's it at? There it is. So I'm going to move that to online tests. And I'll move it before test 5. All right, that should take care of that. All right, so does anybody have any questions while we're waiting for people to show up?
I sent you an email a bit ago about this project that I was doing in another class. And I was just wondering if it might be like an after class. Oh, no. The email was very confused. I'm still confused, but I think I understand a little bit more.
I do remember that email.
And I'm just going through it because, yeah, we're still working on that project. It's taking a very long time, and it's at the point where I think we need some physics involved so we can figure out.
Yeah, that's no problem. You can talk to me right after class. I'll give you as much help as I can. I remember that. I thought I had replied. I'm pulling it up now, but it's not even showing on my in my mailbox. Microsoft doesn't have their system streamlined as well as it is, so like as well as it should be. I've got a copy on my Microsoft Outlook. I've got a copy on my laptop computer, a copy on my desktop computer, a copy on my phone, and then a copy in my office. And somehow stuff gets lost in between those. Like if I answer it in one place, it doesn't go to the other places. But if I answer it in none of the other places, then it goes to all of them. So I'm always missing emails. So yeah, I will certainly do that. That's no problem. The midterms also under reported assignments. Go ahead, Victoria. I'm sorry.
Oh, no, I was just saying thank you.
No problem. The midterms also under reported assignments. Okay, I'll fix that next too. Thank you. Let me make a note of that so I don't forget. Midterm. All right, so we have finished chapter 14, and we're going into chapter 15 tonight, and that's about waves. It's actually specifically the chapter is just called, I think, wave motion. Yeah, wave motion is the name of the chapter. And I'm not going to do as much derivation as I normally do, just because I need you to be able to sort of see what you did, like in chapter 14, how, I showed you how to solve the differential equations. That's not what I'm testing you on, but I showed you how, and then I gave you the solutions that you can use. Well, we're going to do the same sort of thing with wave motion in that your book is going to show you derivations of how to come up with a wave equation. It's going to show you derivations of how to come up with the velocity of the certain types of waves. But my more important issue that I want you to make sure you guys can handle is just applying those formulas, because that's sort of one of the hallmarks of a student of science is you don't have to reinvent the wheel every time. Now, you should not feel very confident in applying a formula that you can't come up with on your own. So I certainly recommend you try to go through the derivations and then even try to pull it off yourself. But the biggest thing is, can you then know how to apply them? Because the derivation is where you learn when they're applicable, when they're not applicable. So we'll go over that. I'm going to go over several other major concepts that are in here that you need to understand: parts of a wave, longitudinal versus transverse waves, all that sort of stuff. So that's really what I'm shooting at for this chapter. I think it's going to take me 2 whole class days. So today and again Thursday, we should be finished with chapter 15. And then next week, it looks to me like we're definitely going to have time to do chapter 43. So chapter 43, which was at one time listed as extra credit, I'm almost 99.999% certain that, and in other words, it's definitely going to happen. But chapter 43 is not going to be extra credit now. It's going to be a regular assignment. I'll still leave it on the same due date, which is like 12/15. But we'll cover that next, and that'll give us plenty of time to start prepping for the final and all that good stuff. So anyone have any questions on anything? All right, so let me start off by giving you an idea of a definition of a wave. A wave is sort of like oscillatory motion in that it's some oscillation that's going on. A wave is really a repetitive process that, in other words, it repeats itself over and over and over again, but it repeats itself not only in time, like the harmonic oscillator does, its motion repeats itself in time. Well, it also repeats itself in space. So in other words, if you take a photograph of a wave, that's an instant in time. And what you'll see is a crest, a trough, a crest, a trough, a crest, a trough. So it's repeating itself in space as well. And it carries energy from one location to another. It doesn't necessarily carry mass from one location to another, but it does carry energy. And in that sense, even a wave like you do in a football stadium is a wave, because for whatever reason, psychologically speaking, when the person next to you stands up to do a wave, you instinctively do the same thing. So what's going on is a wave of potential energy is going around the stadium. As you get to one person, that person decides to stand up. That increases the potential energy of that particular person. And then as you're standing up, the person next to you decides to stand up. That increases their potential energy, and you start to sit down. And then another person next to them starts to stand up. So the net effect is that potential energy is going all the way around the stadium, and it'll go several times. Now, it's not a true mechanical wave because there's nothing that requires humans to do this. We just do it. But it is a wave in that sense. So not only that, it's also important to know that waves occur in many different ways in many different areas, and are applicable in many different situations. And the mathematics and physics of them is the same, basically, no matter what type of wave they are. Okay. So I want to talk a little bit about that, and I want to talk about the types of waves. So one type of wave is a transverse wave, and that's the one. Well, I'm going to save some information later, but ocean wave or a water wave in a sound sort of looks like a transverse wave, meaning you see the level of the water going up and down, but the wave is actually traveling left and right perpendicular to that direction. That's what transverse means. Okay. Now, longitudinal wave, on the other hand, is one where the vibration and the propagation, that's the fancy word for the direction of travel or the traveling, the vibration or oscillation and the propagation are in the same direction. So two more typical examples would take a spring or a slinky. And if I take a slinky, and slinky is just a big spring, it's like that big around, and I attach it, pull it sort of taut and attach it to that distant wall, and I give it a shake like this, and I continue shaking it, what's going to happen is when I lift up this part of the slinky, the tension in the slinky is going to pull the part next to it up, and the tension in that part of the slinky is going to pull the part next to it up, and so on and so forth, until what ultimately happens is I get to the top, and then I start going down. Now that ring that was right next to it reaches the top and starts getting pulled down, and the ring next to it reaches the top and starts going down. So what you end up getting is a wave, a peak like this, that is essentially traveling in the direction of propagation. The oscillation of the mass, the particles of the spring, is actually perpendicular though. So that's that's a transverse wave. Now, in a longitudinal wave, we can also demonstrate that nicely with a slinky. So now I'm going to imagine a slinky or a spring, and I pull it, again, pretty taut off to a distant wall. And this time, instead of actually oscillating it up and down, I'm going to give it pumps this way. Okay. So if I give the slinky a pump forward and backwards like this, what's going to happen is as I push the slinky this way, all these separate rings of the slinky are going to come together and create a compaction. And all those rings of the slinky will be really close together, and then they'll start to move off with their momentum. As I start to pull back, that's going to start to spread the rings, causing not a rarefaction, which I thought would be the appropriate word, but a rarefaction. That's the actual word that you use, rarefaction, not rarefaction. Okay. So contraction, rarefaction. Okay. And then you do it again, push back this way, you make another compaction, and then another rarefaction, compaction, rarefaction, compaction, rarefaction. And what you're seeing is the oscillating is going this way as the wave is also traveling that way. And that is, in fact, a longitudinal wave. Okay. Sound is a longitudinal wave. And you can certainly see that in order for a longitudinal wave, we sort of need some particles, or at least I can feel and understand that. How are you going to make compactions and rarefactions without any actual material there? But what might be a little less obvious is you don't have to have any kind of matter for a transverse wave to travel. Now, there are certain types of transverse waves that need material, like you can't have a water wave without water. But oddly enough, you can have an electromagnetic wave without matter. Okay. You can't have a sound wave without molecules of air or atmosphere or something. So, that's sort of the irony when you're looking at a sci-fi movie of a battle in space and you hear all these cool sounds. You're not going to hear any sounds in space. The only thing that could possibly happen is maybe a wave hits your compressed air situation inside your module or inside your cockpit, and that wave makes a vibration on the actual panels of your windows. That could be construed as a sound hitting your window, but you're not going to hear any explosions going from point A to point B because the matter doesn't exist between you and it. The space is really, as in most places, is as much of a vacuum as we can make on the surface of the earth, where in some places it might be as many as a few hundred molecules in a 1 meter by 1 meter by 1 meter wall, and that's actually pretty densely packed for space. Okay, so those are two types of waves. I've explained sort of how they require medium for the longitudinal wave, but for the transverse they may or may not. And I'm going to talk about the parts of the wave, but I'm also going to talk about some other instances where we have waves. So for instance, we have waves that come from earthquakes. So an earthquake can be, for instance, two adjacent layers that have a great deal of stress pushing. So this one's pushing this way and that one's pushing that way, only it's not budging. And then all of a sudden something breaks way, and it does. Okay. When it does move relative to that, that's not only going to cause motion of two adjacent surfaces of the within the earth, but it's going to cause vibrations and friction and stuff like that. That can be the epicenter, or will be the epicenter of an earthquake. And that earthquake has the ability to put off both longitudinal and transverse waves. The transverse waves they call shear waves, or S waves, and the longitudinal waves they call P waves, which we interpret in physics as they're calling it pressure waves, but I was told by a geologist they call it primary wave because it is the one that gets to the detector first, because it's faster. I'm not sure about that, but that's what a geologist told me. So I'm assuming they certainly know their field of geology better than I do better than I know their field of geology. So I'll let you figure that out if you become a geologist. But either way, both types of waves come off of a earthquake, and that's very telling because we can have a wave, for instance, created right up here on the Earth, and it's going to go in every direction, straight down, straight this way, straight up, all that stuff, every direction. And in fact, we've got detectors all over the surface of the Earth, so they'll pick it up. And obviously, the farther away you are, the later it'll come after the actual earthquake. And the farther away the detector, the less powerful the shake will be, but it'll still detect a lot of them. And over time, through a give and take of model versus theory versus observation, so on and so forth, we've figured out basically what the structure of the earth is to a pretty good degree of precision. And we know, certain types of rocks are in this area and certain types of rocks are in this area. We know they have different densities, different hardnesses, different bulk moduli, stuff of that sort. And because of that, waves travel at different speeds and different densities and different moduli. And they end up following, in fact, curves. And if we use that idea of how things are going to behave when they run into different densities and different moduli of elasticity, then you get ideas of what kind of paths that a particular type of wave, whether it be an S wave or P wave, leaves an earthquake with. And then we compare that to what we see at the actual detector level, and we fine tune our models of what the Earth is made of and get better trajectories for those waves. But over time, over hundreds of years we've been doing this, we've managed to make out the point that it appears every time you have an earthquake, certain areas on the earth with respect to that area where the epicenter was are sort of forbidden from getting any S waves whatsoever. Now, S waves, we know, cannot travel through a liquid. As you probably can imagine, an S wave is sort of what a transverse wave is, which is sort of what again, I'm saying, what an ocean wave is. So you might be a little confused, but this is a wave that we're talking would be under the surface of the ocean, right? There's a definite discrepancy between the way the ocean behaves at its surface right along here versus way down here, some distance halfway between the surface and the bottom. So in fact, the difference is a slight asymmetry. If you're down here halfway down, okay, and you're this molecule, well, yeah, this molecule right next to it is pulling it this way, but on the opposite side is another molecule pulling it this way. And a molecule up here pulls it this way, but another one pulls it this way. And another one over here pulls it this way, and another one down here pulls it that way. So the net effect is that molecule is free to move wherever because it's got an equal pull from every direction, the net pull being 0. Now, when you get to the surface, that's different. So a molecule right here, for instance, has this molecule pulling down and nothing to counteract it. It has this molecule over here pulling this way and nothing to counteract it. And this one over here pulling this way and nothing to counteract it. So you continue on over and over and over. And what you see is water has some sort of surface tension that keeps it from just randomly picking up a single molecule of water off the surface of the water. The water is going to come up with it, and you can see it like if you slowly dip a candle wick in the water and then go to pull it up, you'll see the water welling up beside it due to cohesive and adhesive forces depending on what material you use. So that surface tension is what actually allows you to have a transverse wave on the surface of an ocean. But you can't have that under the surface of the ocean. So the same thing happens with liquid inside of our Earth. And from that, we've been able to map out that our outer core of our Earth is a liquid. And that matches our models of what we think the pressures and stuff are supposed to be like there. But it's really wonderful to see that you've got, material science telling you how matter behaves given the type of material it is, whether it's carbon, nickel, iron, aluminum, whatever. When we look at the material science of that and put it under the conditions that we suspect it is based on our hypotheses and even theories, then we expect it to be a liquid. And then lo and behold, our data comes back and tells us from the monitors on the surface of the Earth that that's completely consistent with where the S waves are stopping. Then you get a great deal of confidence. And the more sciences that point to the same fact, the more confident you are that you're right about it. So we're now convinced definitively that the Earth is essentially a solid material with a liquid outer core, and then without ability to actually detect it based on the detectors, there's in fact inside of that a solid core inside of the liquid core. That one we know from basically the ideas of Galileo and Copernicus, where the laws of physics are the same sort of for all of us. We're not a special place in the universe, and there's not special laws that just apply to us. Therefore, whatever we see applying here out on the surface of the Earth should apply at the center of the Earth as well, and in fact, inside of any other planet. So when we actually put nickel and iron, which is more or less what the core of our Earth is made up of, when we put mixtures like that under the pressures and temperatures that they're subjected to within the inner part of the core, it turns out that those materials go from liquid to a solid, and in fact we expect a solid core to be inside the liquid core, but that's one you just can't detect because if once you lose the shear wave going into the liquid, you can't get it back again just because there's a solid in there. So and even if it did, it wouldn't be able to escape. So that one's a little harder, but we're still really confident that's what it is. So that's some of the applications of these waves. It's really useful. That being said, I need to teach you a little bit about waves. So I've already taught you what longitudinal waves are. They're the ones that vibrate or oscillate, I should say, and propagate parallel to one another. And transverse waves Notice you can think trans like you're transiting across the highway. They actually oscillate perpendicular to the propagation. So perpendicular to their velocity is what they vibrate. So along with the idea that a wave is a phenomena that repeats in space and time and delivers energy from one place to another, helps you see some of the waves. And I'll be discussing other waves, pressure waves, stuff of that sort as well. But let's start off with the parts of a wave and draw them. So what I'm going to draw first is a typical transverse wave. And I'm going to draw this as if it is a wave in time. No, I'll draw this one as if it's a wave in space. So I'm going to say this, for instance, here is y. Now that could be, I'm going to use the amplitude of the wave to be in the direction of up and down y. Now this y might be in meters if you're just talking about, for instance, a water wave, but at other types of waves, you're going to find different things. So I'm going to say this right here is, say, the x-axis. And let's take sine as a typical scenario. So a sine wave would look like this. And these are all supposed to look perfectly identical. Obviously, I'm drawing it by hand, so I doubt it's going to look perfectly identical, but it should be coming pretty close. Now, looking at this as a point in space, this is a long space. This is a snapshot, meaning no time is passing here. So we don't really see the wave moving. If we were watching it in time, we would see the actual wave moving this way or that way or something like that. Variables that you need to know are this one, which goes from the equilibrium or midline up to the crest, and that's what that's called, is a crest. Or this one, which goes from the equilibrium or midline to the trough, and that's what this is called. It's called the trough. That distance is called the amplitude. And I say distance, and I really want to put quotation marks around it because it's not necessarily a distance. For instance, if we have a pressure wave, pressure waves are waves that we use in times of war. It's what Timothy McVeigh used when he blew up the Murrah Federal Building. A giant pressure wave was created by his bomb that actually lifted the building up and then dropped it. And then it was hit by a second reflecting wave, and that caused the whole front of the Murrah Federal Building to collapse. And of course, it also resulted in him going to prison and I think ultimately the death penalty. So a pressure wave actually has an amplitude that is equal to a pressure. So in other words, the units for the amplitude of such a pressure wave would be newtons per square meter or force per area. Okay. If you're talking about an electromagnetic wave, which is what light is, then the amplitude, actually there's two of them. There's an amplitude before a wave is oscillating one way, and then perpendicular to that is another oscillation, and then perpendicular to both of those is the velocity. And the amplitude of one is the electric amplitude, and that has units of volts per meter or newtons per coulomb. And then the other one is the amplitude of the magnetic field, and that one has units of Tesla. So you can see the amplitudes can actually have a lot of different units associated with it. Now, we also have things like if we wanted to measure the distance, say, from this crest to this crest, that is a variable that we use the symbol lambda to represent, and lambda is called the wavelength. And lambda has units of, or dimensions of length, which has units of meters. So that's why I'm using, sometimes I use like F over A. That's me saying the dimensions. And then I use newtons per square meter. That's me saying the units. Same thing here. Length is the dimension, but meters is the unit, but they come up in kilometers and all sorts of stuff. For instance, the wavelength of the radio station 850 AM has a wavelength that's about 5.5 football fields. 4.5 football fields, excuse me. So you can imagine that's obviously approaching kilometers in distance. We have wavelengths that are actually on the average maybe nanometers and stuff like that as well. However, another way of measuring the wavelength is from the trough to the trough. And then a third way is from a point to an identical point. Now you might think this is identical, but notice this one has a negative slope and this one has a positive slope. So they're not really identical, but this is, so that's another wavelength. Okay. Now, if I take a picture of it, what we see here is this is the actual repeating itself in space, right? I'm going along at some place that I called the arbitrary origin. And if I could walk on water, I would actually walk up here and say, okay, I'm at the high point, that's the crest. And now I'm walking down here, I'm at the midline, and walking down here, that's at the trough, and so on and so forth. And I see it repeats itself over and over and over again in space. So this is repetition in space. Now, if I actually consider a graph of the wave in time, so let's say y again, which is going to be an amplitude, but this time it's going to be in time, then the wave might actually look like this. And what you see is at 0 time, I actually was at a midline. And then a few seconds later, I was at a crest. A few seconds later, I was at midline. A few seconds later, I was at a trough. A few seconds later, I'm at midline again. And in fact, this time right here is called T, the period. So T equals the period, which T would have dimensions of time or seconds. Okay. Again, that's the dimension, which we use capital T or sometimes lowercase t. And then this is the time, the unit, which would be seconds, years, so on and so forth. I think you can tell by looking at this thing in time would actually be moving with some velocity v. And in fact, a wave will travel a distance of one wavelength in a, let's make that a U, a unit of time called the period T. Okay. So that's a fundamental rule. The wave is going to travel a distance of one wavelength in an amount of time of one period. We know that velocity in general, comparing it to speed, is just distance traveled divided by the time taken. So can anybody give me the kindergarten version of a wave equation? In other words, can you make use of that paragraph I just, or that sentence I just wrote, and this formula and the symbols that you've been taught? Can you use those to come up with an equation for the velocity of a wave? Go ahead. I missed part of that. Was that Aaron? Who said that? Abby? Oh, yes. Someone said lambda over period. That's Jared. That's exactly right, because the distance traveled is one wavelength and the time taken is one period. So that is one of the kindergarten versions of the wave equation, and it's very important. I leave it equals there because I got to introduce something else too. There's also a quantity called the frequency. The frequency of a wave, which by the way, we use the symbol F for. The frequency of a wave, F, is the number of cycles or wavelengths that pass a single point every second. Okay, so the frequency of a wave is the number of cycles or wavelengths that pass a single point every second. So let's see this. Let's see if you can figure out what this is. Let's say the period of a wave is 4.00 seconds. How many waves will pass a point each second? Can anybody tell me that? How many waves? It takes 4 seconds for a single wave to pass you. That's what the period means. And so I'm asking you, how many waves pass you in a single second? Anybody have an idea?
1/4 of a wave.
Very good. I usually have to take the time to put how many in quotation marks to help people. But yes, that's exactly right. And what you just said is the definition of frequency. So you said the definition of frequency gives you that the frequency is 1/4, right? Now the frequency has units of cycles per second, or what we call just plain hertz. But like I said, that would also be written as 1/4 of a cycle per second. So sometimes you'll run into old books and it'll say 0.25 CPS, especially in the Navy. You'll see that on occasion. But that literally means cycles per second, which means hertz. Now, this isn't a coincidence. This is not a coincidence. In fact, frequency is 1 over the period, and of course that means the period is 1 over the frequency. Okay, so now that we look at that, I see 1 over period here and I see 1 over period here. So what's another version of the wave equation? Instead of using period, let's use frequency, and what would you get? Yes, lambda times F. And this is the more usual version of the elementary wave equation, or the kindergarten wave equation. They usually say velocity equals wavelength times frequency. Of course, they're both right, and that's all well and good. But now we've got some terms that we know of. Of course, we still know from circular motion that omega is equal to 2 pi f. And we already knew, of course, that frequency is 1 over the period. So those are things we already knew. But I thought you might not be able to necessarily recall that in this seemingly somewhat different realm, but you're going to see they're very, very similar realm, because before we were doing oscillatory motion by recognizing it as x equals a cosine omega t plus phi. You're going to see a very similar relationship for wave motion. Okay, where we got to take in not only omega chi, like what this graph shows, but also some other factor times x. So that's where we're ultimately going. Now, that's some of the characteristics of waves that we need to know. Obviously, there's more things as well. Your book, for instance, tells you how energy is related to velocity, how energy is related to density, how energy is related to frequency, to amplitude, all that good stuff. But to give you some examples, for instance, let's think about this. Let's call this example 1. Let's say if a wave has a wavelength of 5.00 meters and a frequency of 3.00 hertz, how far can the wave travel in 1.00 seconds? That's easy enough, right? Hopefully y'all figured that out. Anybody have an idea? I kind of hid, yes, that's right, Jared. I kind of hid, but I was asking for velocity, but I wanted you to see that, or to not notice that on purpose. I was hoping you wouldn't notice it because I didn't really want you to blindly just apply a formula, but I wanted you to think, hey, this thing says that it has a frequency of 3 hertz. That means 3 hertz or 3 waves, 1, 2, 3 is going to pass by in a single second. Well, each one of those is 5 foot, 5 foot, and 5 foot. So we see that it should actually travel a distance of 15 meters in that, or 15 meters in that 1 second. So yes, that is in fact 15.0 meters. And in fact, what you would do is you'd say, okay, velocity equals wavelength times frequency. Wavelength is 5.00 meters. Frequency is 3.00 hertz. And of course, a meter times a hertz just becomes a meter per second, which is 15.0 meters per second. And now you multiply that by 1 second and you get 15 meters. Okay, that's sort of the way I'd prefer you to do it, is what you did the first time was just concluded 15 meters, and then you could retroactively look back at it and say, oh, well, if it did that in 1 second, it must have been traveling at 15 meters per second. And then you'd see how much sense this stupid equation makes, right? The velocity equals wavelength times frequency. So any questions on that? All right, so with that in mind, now I want to go a little deeper and tell you your book actually does a derivation for many of these speeds. And like I said, it does derivations for the wave equations and stuff like that. I'm not so much interested in covering that part for you, but I definitely want you to read it and do your best to understand how they get what they get. But what I want to do is give you some results. So for instance, one of the types of waves we talk about are waves on a string. So waves on a string, and this is not as abstract as you're thinking. So let me give you an idea. You've probably done this before. You've probably taken a rope and swing it up and down. And if you swing it just right, what you'll see is the wave, the string goes like this and this and this and this and this and this. And if you wiggle it just a little faster, but just right, then this half will go up when this half goes down. And this half will go down while this half goes up like this. And then you can go further still and it'll get where there's, this third is up and this third is up and this middle third is down. That's a wave on a string. What's really happening there is you're timing the sending of the wave by doing this at just the right frequency. You're sending it so that what happens is a pulse of a wave comes this way like this. Yes. Oh, Rebecca, you got your sound on, hon. Sorry, I don't know why I called you hon. Just ignore me. Anyway, so crest is going like this, and just at the time that it gets to that wall, remember that wall is, or whatever it is locking that down. So the tension in the rope is going to pull up on the wall, and then according to Newton's second law, or excuse me, third law, the wall is going to pull down on it. That's not a problem, Rebecca. The wall is going to pull down on it and cause the waves to flip upside down. And just as that happens, another wave upside down will hit there, and it builds basically a standing wave pattern. So it constantly looks like this, say, the sine wave, or it constantly looks like this, the half of the sine wave, or it constantly looks like another. Those are called standing waves. And when you have the standing wave, what that means is the distance from one node to the other node, the two parts that are sitting perfectly still, that is a half even or a half number of multiples of the wavelength. Okay. Well, that still sounds pretty abstract. You're still like, Mr. Younger, you're talking about stupid crap kids do on a playground. That doesn't matter to anything. Well, then you take something like, I've got a banjo right here and I pluck a banjo. That's exactly what happens. You pluck it at its fundamental frequency. So for instance, D4 is 293.56 hertz or something like that. I pluck it and I'm getting that first harmonic, which is also called the fundamental frequency. And it's not an overtone, it's just called the first harmonic or the fundamental frequency. But by plucking it, so you can also pick out a multiple of that, which is where I have a whole wavelength, and that's called the second harmonic or the first overtone. And then I can pluck it still, and then you'll have 1.5 wavelengths going that distance, and that's called the second overtone or the third harmonic, so on and so forth. So this is stuff that happens in everyday life. This is stuff we'll do in our labs next semester with microwaves. This is stuff that happens with water waves. If you're ever like sitting by Rudy Inlet, and you'll see all these waves coming, and you know they're all 1, maybe 2 feet tall at most, but then every now and then what you'll see is a wave go and it's like 5 foot or 6 foot tall. What happened is all those waves just interfered at just the right time where all their crusts lined up, and you got a 5 foot tall wave because maybe it was 5 1-footers or 2 2-footers and a 1-footer or something like that. So that's how waves interact. There's a principle called the principle of superposition that basically says when two waves run into each other, their amplitudes at each particular point just add. So if I had a little 1-inch tall wave here that was running over a 2-inch tall wave at exactly the same time that their peaks are aligned, then that middle part will be 1 inch plus 2 inches or 3 inches tall. And then those parts where they have no overlap, it's just going to be a little bit of whatever the height beside the peak is plus whatever the height beside the peak is. That's what waves do when they interact. And then after they pass through each other, they're like nothing ever happened. So the 2-inch wave just continues on this way and the 1-inch wave continues on that way. So that's some of the fundamentals. Well, when you're dealing with that, it's helpful to know what the velocity of that is. What parameters does it depend on? So let me go back to my equation sheet and basically my document cam. Well, it turns out that the velocity of a wave on a spring is, or on a string, S-T-R-I-N-G, not spring, is equal to, your book uses F sub t, and I get why, because this t is being used for the period, but I always use tension. So I'm going to write t here and put little quotation marks around it just so you'll realize it's tension. And then it's divided by the mass per unit length. So I'll say where T equals tension. So that's the tension in the string. And mu is equal to the total mass of the string divided by the total length of the string. So the tension should have units of newtons, and the mu should have units of kilograms per meter. Okay. And it turns out in general, the velocity of a wave is the square root of an elastic force parameter divided by an inertia parameter. So that turns out to be the fundamental idea for all the velocities. You can see here, yeah, the tension is the force of elasticity, if you will, that, you know, causes one part of the string to hold tight to the part next to it. And the inertia part is mass. Inertia really is mass. So this inertia parameter is mass per unit length. So that means if you want to look at, for instance, the velocity of a wave in a rod, well, it's going to be the elastic moduli over the density. E equals the elastic modulus, which is covered in chapter 12, which is just an extra credit chapter for you. If you go into engineering, you're going to learn a lot about moduli. So this is the elastic modulus. And I'll give you a little bit of a brief intro to moduluses in a second, or moduli, which is the plural. And if you want to know, for instance, the velocity through a fluid, that turns out to be the bulk modulus divided by the density. So whatever material you're using has a elastic medium, like an iron rod. You could look up E for iron, and they would give you an elastic modulus for iron. You divide that by the density in kilograms per cubic meter of iron, take the square root, and you'd have the velocity of a wave in a rod. Now, you might not think that's all that important, but I tell you what, I had two engineering instructors at NC State. Well, one of them was actually a former student and just a person I got to know a little bit. And the other one was an instructor that I got to know. And his name was David Fisher, and the other one was Holt. And there was a third guy who had retired. All these people had Holt doing a PhD dissertation in engineering, in structural engineering. And what he did was he discovered he could do what's called a Fourier series, but it's a Fourier series on a terminating function. In other words, you know how you could, well, you not necessarily know this about Fourier series, but in general, just like a bunch of polynomial terms can add up to give you sine, or can add up to give you cosine, like I showed you in our last class. Well, it turns out there's something called a Fourier series that can be used to represent functions as well. And in fact, that's normally functions that repeat themselves. So like you can build sine out of a series of sines and cosines and stuff like that. And that's a Fourier series. Well, no one had ever done that for a wave that terminates, like that underdamped case for the harmonic oscillator, the damped harmonic oscillator, where it goes up and then the amplitude gets smaller and smaller and smaller. No one had ever been able to do that and break it down into various frequencies. Well, this guy by the name of Holt, whose first name I forgot now, he did his thesis on this and figured that out. Well, the guy Fisher and Holt and the other guy, who was one of now the emeritus faculty at NC State, they created a company where they use that very technology. And now you can go, for instance, to a hotel that was built on the ocean front, and maybe it was built 75 years ago. The blueprints are long gone. You have no idea how deep the pilings are that they stuck into the ground to build it. Maybe you want to update your hotel by building a couple more floors on it. Well, there's engineering rules and you know, methods that require you to know things about the foundation. And if you've lost all that data, you would seemingly not know what the heck to do. So these guys took that technology and they put a little cheap acceleration sensor on the actual piling above the ground, and they just hit it with a sledgehammer. The wave goes down and attenuates, it's shrinking over time, and then comes back up. And from that, they can actually break up the wave into various frequency components and tell how deep the piling is. They can even, you know, detect problems with pilings breaking, stuff like that. But that's one of the major feats, is being able to figure out how long the pilings are, what they're made of, all sorts of good stuff like that. And that's all because of that technology. So guess what? that ultimately resulted in them making a multi-million-dollar company. They now are asked to fly all over the world to do engineering speculation or specifications on a building and stamp it saying, yeah, this building meets the criteria to add 3 more floors or whatever. So yeah, this stuff comes in super handy, and it's all about these velocities of these waves. And you know, something as simple as hitting something with a hammer can tell you something beautiful that can help you make more money. So yeah, there's a lot of cool stuff with that. So that is waves on the string. I've given you waves on a rod, and I've given you waves through a fluid. I will tell you, for instance, also that the wave through a fluid, if you've ever taken a scuba diving class, or you ever do so in the future, you'll hear something about sound being omnidirectional. This is exactly why in scuba diving class you learn that sound is omnidirectional. You might think, you know, clearly a denser fluid would make the wave travel slower, and that's, you know, that says this. See, the density is down here in the bottom, so if density goes up, velocity goes down. But the way we tell directions for sounds with our head, and of course people with only one working ear can't, except through experience or something like that, or some other senses that we haven't detected yet. But basically what it does is your brain picks up the signal coming to your right ear, and if that's a little earlier than the signal coming to your left ear, then it knows that the source of the sound is closer to the right side of your head. And over time it's sort of worked out and got a pretty good experience in that, and your brain quickly can say, oh, it's coming from, you know, maybe about 45 degrees ahead, but on the right hand side. So you can do that and you can figure out stuff. Well, here's the problem. When you go to under the water, yeah, the density goes up by about a factor of 1,000, but it turns out that the bulk modulus of water is about 1,000,000 times the bulk modulus of air. So you basically get 1,000,000 over 1,000, take the square root, and lo and behold, you get a velocity of sound in water that's way too high, so that your brain can't detect which one was first. To the brain, the left ear and the right ear, sound was reached at each of those ears at the same time. So that's why it's omnidirectional. That doesn't mean sound's not useful underwater. We carry wrenches with us or knives or stuff like that, and we hit them on our tank to get people's attention. Not really for this reason, but this is a funny reason. So for instance, if your friend is standing there making googly eyes or stupid faces at you about something funny, and you see this really angry great white behind them, you don't necessarily need him to know which direction the sound's coming from as much as you just need him to hear the sound. So you've got a little advantage in this, because you can make the sound and he'll immediately hear it. He won't know which direction it came from, but that'll entice him to look all around because he can't know which direction it came from, which is really what you want him to do, because if he's looking at you, he's looking the wrong way for the shark. So that's another real life application, if you will, to physics. So with that in mind, we've now gotten a lot of information about a lot of different waves. The things I need to show you, though, is I need to talk a little bit about the modulus, what they are, what the modulus is. So you'll have some sense of it, but this isn't really part of the chapter, but it'll help you if you decide to do chapter 12 homework. So a modulus in general, it's mostly experimentally determined figure, but it's always the stress over the strain. Okay, and notice RESS is in here. Okay, RESS is also in the word pressure. That's my mnemonic that I use. RESS is in the word pressure, and in fact, for many situations, the pressure is just force per unit area, which is exactly what pressure is, which you'll also learn in chapter 13, which again is an extra credit chapter. Okay, so the stress is always the pressure. Basically, it's force over an area perpendicular. So when we're talking about for the rod, say if I wanted to hit that rod with a hammer, okay, if I wanted to hit that rod with a hammer, what would happen is that hammer would apply a force right here, And this right here would be the area A. So I divide that force by the area, and that's my actual stress that I'm putting on the hammer. I mean, on the rod. Okay. Now the strain is a change in something divided by the original something. So in this case, it would be, for the rod, this would be F over A divided by, and this is the elastic modulus I was telling you about before. In this case, it would be delta L over L0, where this rod has compressed by an amount delta L when the original length was L0. Does that make sense? Speaking of which, I forgot to write this up here. That would have been bad. So today is 11/17/21. And this is PHY 241N05B. All right. So that's the general definition of a modulus. It's always stress over strain, and stress is almost always pressure. Okay. Now, if we're talking about the bulk modulus, then that is force per unit area again, but this is divided by delta V over V0, and that's the bulk modulus. So as you can tell, this is something that you would need experimental data to figure out what the bulk modulus is of various materials. But it turns out there's good manufacturers that do this stuff all the time. For instance, if you're going into structural engineering, there's a handbook of wood products that you can buy. And in fact, if you take wood structures at NC State, you're going to get a copy of Breyer's textbook, and then you're going to get a wood and paper manufacturers compendium of books that have formulas in it. They have all the bulk modulus, the elastic modulus, the bending moment, and all these different parameters for wood. And that's where you look them up. It turns out that the people that sell you wood have a vested interest in giving you that data and giving it to you very well. So you just look that up, and then you can tell whether I can use a 2x4 or a 2x6 or a 2x8 to span an 8-foot gap holding a floor above a 8-foot wide room. Okay, so that's what those moduluses are. So that's not really that relevant to here, but that gives you some idea how you're going to go about calculating velocities of various things. Now, the other things we need to know about waves is what do they do when they interact with one another? And I've already hinted at that. I've told you, for instance, that they interfere or react with one another in such a way that the amplitudes at each particular spot add up algebraically. So that's the principle of superposition. Which is quite different from the geologist principle of superposition. But it's somewhat related, believe it or not. So the principle of superposition just basically says, hey, let's take this wave right here, and let's say it has this particular shape. And then let's take this wave right here and say it has this particular shape. Then the sum of them is really, this is all 0 from here to here. This is all 0 from here to here. And I'm going to say roughly this is 0 from here to here, right? And this is roughly 0 from here to here. So if I go down here, I'm going to say this is my 0 line. And right here, I'm going to add this much. And then on top of that, I'm going to add this much, which is right there. So I just added this distance plus this distance, which I think is, let's say this is A and this is B, right? And I do that with each particular spot. And then I get, of course, this one's only this much. And then this one's only almost the same. So I'm now going to say like this. And then right here, I do the same thing again. And this one's only 0, but this one's like this. So it'll be right about here. So you can see it goes. And the same thing sort of over here. That's what the principle of superposition says. Okay, so I'm literally trying to show you that each little spot adds up conjunctively. And I showed this really narrow for a reason, because I wanted you to understand that this one contributes nothing beyond here, right? So maybe I should have put it a little bit more like that. Does that make sense to everyone? Now, this is the weird part. We might say this one was actually moving this way and this one was moving this way. So after it's all said and done, what's going to happen is this little wave is still going to go like this, moving this way. And this big, wide, fat wave, trying to draw it the same, is now gone by as if nothing ever happened. So supposedly identical. But only when they're interacting do they add it all. That's the principle of superposition. And what that tells you something neat, which I mentioned already before, but if you have a wave that looks like this, and it's perfectly lined up with a wave that looks like this, then you get basically a wave like that. So A plus B is equal to A plus B. So when crests line up with crests, you get constructive interference. That's what's going on here. And when crests line up with troughs, so let's say I've got this wave like this, and let's say now I'm going to try to draw it perfectly lined up. So I'm going to give me some little guides to help me. So I'm going to now say this one goes exactly down one, up like this, then up one, and then down like this. So this one's literally supposed to be the upside down of that one. Then the sum of these two is just flat. So this is C plus D, and this is C plus D. Okay, so this is called destructive interference. Okay. Now, this is also why, if you ever watch Big Bang Theory, there's one early episode where they go to the movies together. I think it's Leonard, Rajesh, and Wallowitz all go to the movies, and they're watching like an Indiana Jones or something. And in that particular episode, Sheldon walks in and starts going caw 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 caw. And he does it in all these different locations. What he's literally doing, though, is inside of a room, each spot you send out waves from, they're going to bounce off all the walls in the room and come back to you. And if they come back in a destructively interfered way, then you're not going to get any sound. So he was not only trying to see, do sounds come back to me at this particular location, he was also trying to check the various frequencies. So go, nope, and yeah. So he's trying to shoot all the different frequencies. And if he finds one that has dead sound at a particular frequency, he's going to avoid that seat. So, and that's not unlike what an actual architect for an acoustical facility would do. They're actually going to run computer programs where they're basically going to test what the sounds are going to do coming from, say, an orchestra in an auditorium that they build, and try to eliminate as many of those dead spots as possible. So he was looking for audio dead spots by using this principle of constructive and destructive interference. This principle of constructive and destructive interference can also be used to explain, for instance, the little puddles of water right after a rain in a parking lot. If you ever look at those, you'll see they got all sorts of pretty little colors in them. And, you know, it's just crappy mud and tire and rubber and oil and gas and everything else. But what they're actually doing there is light is coming through a surface, and there's a bunch of different chemicals with different densities in there, and each one has a different index of refraction. And when you go from one type of index of refraction to another, you actually flip phases so that you go from a wave being like this to a wave being upside down. And then other types of interfaces, the waves stay the same phase. But at each case, when they bounce off the bottom of a phase, they come back and constructively or destructively interfere, depending on if the distance they traveled is a whole wavelength, then they constructively interfere if they were constructive to begin with. But if they were destructive to begin with and it was a whole wavelength, then they'll actually destruct. But what you're seeing is the varying levels of thickness, because certain wavelengths have certain colors, and that's called the thin film experiment, or a thin film analysis. So basically you can use that to determine, you know, basically what densities of materials are there or how thick the layer is. You can also use the same principle to take something like glass, say, and lay it on something really, really small, let's say a carbon nanotube. Okay, that's literally a physical object that's a string of carbon molecules, or a string of carbon atoms making a big long tubular molecule. But literally it's on the order of the size, its diameter is on the order of the size of atoms. So you can take one of those and prop up a little glass, and what you'll see is these little rings of light, where one ring is destructively one particular phase of light is interfering constructively with another. So you get a bright line, and that tells you basically how far apart the glass is from the table, because when the light bounces off, it's going to recombine with the reflected light. And if that is a whole wavelength, then it'll be constructive interference. If it's a half a wavelength, it'll be destructive interference. And you can use that to measure the thickness of the nanotube. So neat little things like that come in. Now, the other part I wanted to talk to you about is about this, and these are questions I've actually seen. I was employed by Pearson one time to write a solutions or a physics book. It's actually to do a solutions manual for a physics book for taking the ACT and no, the LSAT. That's what it was. I think that's the test for people to become lawyers. So I had to make up a bunch of different questions, and in other ones, I actually had to take the questions and write the answers. And one of the questions I saw was pretty interesting because no one ever covered it for me. But let's imagine this. Let's say you have a thin rope.
Every possible way to kill a man.
Let's say you have a thin rope. And what I mean by thin is the mass per unit length is small. So mu is small. And let's say it's connected to a thick rope. So mu is large. So what we'd like to know is what's going to happen if a wave travels along this and then hits that one, or if a wave travels along this and hits that one. But as a first order understanding of this, we need a little deeper understanding. So I'm going to consider two scenarios. Let's take a thin rope connected to an anchor in a wall. Now, I've already hinted at this. So when we have a pulse doing this, right? What's going to happen when this pulse, which is moving at some velocity v, when this pulse gets right here, what's going to happen? Anybody have an idea? It's actually going to turn around and go back. But what I want you to consider, so yeah, stopping is right, but it's actually going to bounce back. It's going to reflect off of that. But do you think it's going to reflect back upright or upside down? So maybe I asked it a little too non-specifically. So that's the real question. Will it bounce back upside down or right side up?
Upside down.
It will upside down. So what's going to happen here is this little portion of the string is going to pull basically upward on the hook. The hook is going to respond. the hook is going to respond by pulling downward on the little segment of rope. That's going to cause the rope to ultimately turn the hook upside down. And what you'll get is a wave coming back backwards, or coming back upside down on the way back. Okay. So that's what's one thing that's going to happen. Now there's something that's a little less extreme than that, and that is this scenario. Now let's imagine, again, a thin rope. Again, it's going to be connected to a hook, but this time the hook has this neat little mechanism where it's not, you know, completely massless, but it's really, really light and got some really smooth kick butt looking bearings in there. And it's free to slide up and down on this pole. So now when I have this pulse going this way, what happens when the pulse gets here? Again, I'm thinking in terms of upside down, right side up. Is it just going to die out and you know, come to a stop completely and nothing go on? If so, where's the energy going? Anybody have any idea on this scenario? So this was real questions that they had on the LSAT and the MCAT. The MCAT's the one for the medical field. And I think the LSAT was the one that was for the legal field, but I know it was the legal and medical field that I was doing it for. So with this scenario, it's sort of like this because it has some mass. So it has some reluctance. So there's definitely going to be a little component of it wanting to slow it down. But in fact, in this case, what's going to happen is you're going to get a wave that's lost some of its energy, but it's right side up. Because what happens when this little piece of rope right here pulls up on it, this thing has the ability to go up. And in fact, it's going to steal some of the energy of the wave. Therefore, the wave will be shorter. And in fact, the wave will come back going the opposite direction, but still right side up. So now you can sort of make some sense of what happens here. This is sort of like that. So if you send in this ginormous wave or pulse, if you will, going this way, when it gets here, it's going to have some reluctance to move up and down. So it's going to want to do like this, but it's also going to win by making this move a little bit. So what ultimately happens is you get a wave now going this way, and then a slight small wave going back this way. So this is the results after it collides. Okay. If you did it the other way, believe it or not, the same thing happens, only the bigger one gets a smaller wave. And of course, the smaller one actually gets a bigger wave. Neither ones will be as big. So if I did, for instance, a pulse like this, then moving the wave this way, then what would happen is it would reflect back just a little bit. So you get an itty bitty thing like that. But you'd also get a considerably bigger wave on this side. And this one's now going this way. This one's now going this way. But I'll tie it together so you'll know it's after the effect by putting the red on it as well. So those colors meant something to me in terms of helping you understand what was going on. The blue or black is the initial state, and then the state with the red in it is the final state. So, and I used the separate colors to show what was the result of this. So that's something that happens when waves encounter different media. Now, the thing that I kept hinting to you about with regards to music are if you have, for instance, the nut, and then there's this little bridge back here at the back on a guitar, you can pluck it so that it does this. And you know our typical wave is the sine wave, so that's one whole wavelength. You can see that this length L is equal to the wavelength over 2. If you pluck it harder, again, the same length. In this case, you're going to see this do this and that do that, in which case L is equal to 2 lambda over 2. Do it again, and you get L is equal to 3 lambda over 2, and that goes on and on and on. This is when you have a node at each end. Of course, you might have a node at one end and an antinode at the other end. For instance, in a pipe organ like this, then the standing waves are this, in which case L is equal to lambda over 4. And then you could do L is equal to 3 lambda over 4. And then you could do that's a whole wavelength there. So that's 5 lambda over 4. So that's what happens when you have one node in and one antinode. This is the antinode. And this is node and node. And of course, you could also do antinode at each end. That's a double open-ended organ, pipe organ as well, in which case you'd have this is one standing wave pattern. That's a quarter plus a quarter. So that's L equals lambda over 2. And you can see you can also go. And now I've got a half a wave plus a quarter plus a quarter. So that's all just like this one, which in this case, it would be half plus half. This would be a whole wavelength. This is 2 lambda over 2. So you can see these are called the fundamentals. And first harmonic. This is called the first overtone. And the second overtone. So on and so forth. But that's actually what happens when you play a musical instrument, is you're setting up standing waves, and these standing waves are basically waves going back and forth, but they're constructively interfering if they're just the right frequency. And when that happens, you get these patterns that look like this. And you can see that obviously, since the velocity, the tension doesn't change, the string doesn't change, so the velocity is not going to change, but the wavelength obviously did. So the frequency's got to change by the same amount. So when going from this one to this one, the wavelength got longer by a factor of 2. So the frequency must have gotten larger by a factor of 2. So from here to here, frequency went up by a factor of 2. And that harmonizes with this note. So this might be 209, or this might be 280 hertz. Right here, well, this one will be 560 hertz. And from here to here, that's going to go up by another factor of 1.5, and that's going to, in fact, harmonize again. So frequency goes up again this time. This time it goes up by 3 over 2. So that's why they're calling them the harmonics. So this is the second harmonic. But that ultimately ties back to the fact that the velocity is equal to square root of the tension divided by the mass per unit length. And that being equal to lambda times F tells you why you have to fret, your string on your guitar or your string on your banjo. You fret it to shorter and shorter lengths. That makes the wavelength shorter and shorter, which makes the frequency higher and higher. So that's good for right now. I've covered a buttload of conceptual material. Y'all are actually in a spot where you can answer all the conceptual questions for chapter 15, but I'll still cover chapter 15 next time. So you're free to go unless you have questions. I think Victoria wanted to ask me some questions about a project. No problem, Rebecca. Otherwise, I will see you guys at lab, or I will see you Thursday.
All right, have a good weekend.
You too.
Okay. So I honestly actually don't even know where to begin.
Okay.
So we have this mousetrap car, like tractor thing that we're building. And it's just been a doozy. So I was just trying to figure out, like, because it has to go, like, we're racing it against another team, and it's just like whoever gets the most batteries in the sled and pulls it the furthest. That's how she's calculating it.
Gotcha.
Um,
So it has a power and a speed
mhm,
as goals. Gotcha.
yeah. Um,
And
yeah.
you're
So
using it, what, like a mouse trap or something to wind it up, or a spring? What are
yes,
you using?
mousetrap, yeah, we have it's kind of a small one though, but yes, it's a mousetrap on it. It's just like my teammates, because I got all the stuff for it and we put it together, and I'm holding it and I'm like, this is heavy. um
I made it
so
where you
I,
share the screen, so if you want to do anything like that, you're welcome to. Uh, the big thing that you're trying to do here is, one, in order to pull heavy stuff, you need a lot of torque,
mhm,
which you know that a mousetrap can give you a buttload of torque.
mhm,
If the lever arm is big enough, right? Because torque is not
mhm,
only force, which obviously the mousetrap can give you, but then you also want to adjust the lever arm so that it can actually be force times lever arm, getting as much torque as possible. But at the same time, you don't want so much torque that basically it spins out instead of speeding up.
mhm.
So you sort of want a bit of mass to it, which is what the batteries are going to supply, but you're also going to want to limit your moment of inertia of your wheels so that they're easier to turn to, but with a grip. Did it give you choices on what you're making your wheels with?
So that's like the biggest thing that we've been contemplating. So I don't know if you're familiar with the Arduino
Yes.
Bobot.
Yes.
Those parallax wheels, I I'm like, I contacted a 3D printing company and I'm hoping to get the like similar ones 3D printed and just put like a rubber around it, because they're thin, they're, the rubber gives enough friction, and they're lightweight. So I was really liking those, but my project people, my
Deadline.
classmates, the deadline is December 7th.
Gotcha.
So we have some time, but yeah, they made like these really big wheels, and they put like these metal ball bearings on it, and it's kind of big, and these huge wooden axles, and it's heavy. And
Have
I
you
just wanted to do some math. I just wanted to try and figure out, like, I don't know. I was
yeah,
hoping to use
well,
physics to hopefully figure out
somebody
what
was
I need to do.
wanting big wheels with big radii so you can get more power basically.
Hmm.
So you might try, this is something that you don't have to make either. You just have to find some old, those small records, like on a record player.
Hmm.
CDs actually work as well. They're thin, flat, can be pretty tall in diameter. You
Hmm.
can use a CD as a wheel, and you can even put just a bead of electrical tape around it, and that might even give you enough uh, stickiness for traction. So those are some options. But yeah, the ultimately what goes into it is you sort of have a F equals KX scenario with the force supplied by the by the mousetrap.
Hmm.
And but at the same time, that force is so hard and so fast, it wants to come all out at once. So you want to try to gear it some way so that you can get it to take off slowly and pick up a heavy weight and then accelerate for a good distance. So
Hmm.
you need some sort of gearing system with that, which I'm sure y'all probably looked at various gears you can find at Hobby Lobby and Michaels and stuff like that.
Hmm. Yeah, yeah, this one is yeah, because they tried to like use Legos and some other stuff, and none of that was working. So I went out, got some balsa wood,
Hey,
and uh put it together. But then I let them start taking control of it again, and it got heavy and it got big, and I'm like, this is not what we want. We want less mass you know, and friction on the wheels. We don't need these big giant wheels, you know, we
Right.
just need, yeah. And the parallax, the wheels, I contacted the 3D printing company to make them bigger, slightly bigger than CD size. I didn't want like record player size.
Right.
But I mean, yeah, because they made like these huge, I mean, they're lightweight, they're 3D printed, but their width is like, why? Kind of thing.
Well,
So
is the stuff they've done to the one that you made, is that stuff that can be undone, even temporarily?
I'm just gonna have to go get some more balsa wood and
Okay. The
reconstruct.
reason why I'm saying is you don't have to kowtow to people that aren't listening to you when you actually have the facts on your side. So you can, for instance, show them, hey, look, here's what I did with my lighter weight. Here's my heavy weight. Here's my medium weight. And if you see that you get more speed and more power with the lighter weight by, a series of experiments, then they got to shut up. And that's really what the project's probably trying to get you to do, is they're wanting you to realize I really got a trial and error, but also because the problems are a little bit more complicated than you can just solve with physics. It's more about applying physics to understand certain things. Like if I change the gear ratio, then that means the wheel is going to spin less times than the actual mouse trap's going to turn. Well, that's not good. Well, what if I do the ratio the other way? Well, then the wheel will turn a bunch of times for one turn of the mousetrap. That's good. That's the kind of physics you're using. And then you use principles like you're shooting for, is low mass means higher acceleration, but low mass means lower friction. So you really have to do experiments to do it. So what you want to do is try various trials of how fast it can go and how much weight it can carry, and then look for the happy medium. Because if you look, they probably gave you on the sheet how they're going to grade it. It might be equal parts how much weight you can carry versus how fast you can go. If that's the case, then you want the dead middle one. You want the one that can carry the middle amount of weight and the middle amount of speed. Does that make sense? Yeah, that's what I would do, and that's really what they're wanting you to do, is come up with some graphs of, and you don't have to have any fancy equipment. You can just literally use a stopwatch that's on your watch, and go across tiles of the floor. You don't even have to measure that. You just count the tiles that are identical and see how far it goes in such and such a time, and then do that again with 9 batteries versus 18 batteries versus 27 batteries.
Okay.
But yeah, I'd check on the scoring, how they're planning on scoring it. Is it, are you better to go carry less weight but go faster? Or are you better to carry more weight but go slower? Or are you equally graded on how fast and how strong your car is?
It's the greater the distance, and also how many batteries. She said that my professor said that she's never had a winning team with more than 5 batteries. So
okay, so and that's good. She gave you a goal to shoot for. You want to shoot for more than 5 batteries. You might not get it, and that's okay. But also they told you something, because the distance she wants traveled, that's not just a speed thing. If you can gear that mousetrap down to going so slow that it keeps pushing that wheel to accelerate, then you can get a lot bigger advantage over the other teams, because the slower that wheel turns, the more force it can actually apply. Because that's another one. Power equals torque times angular velocity. And you have a fixed amount of power. So if your angular velocity is too high, your torque is going to be too low.
Okay.
You remember those equations we did in chapter 10?
Yes.
And a little bit more in 11.
Yes, I remember them. It's just applying it now. I'm like, where do I start? Like, I don't.
Yeah, you can't calculate. That's the big thing. You just got to use things like thumbs up, thumbs down. Let me talk to you in my face instead of my paper here. You got to use things like thumbs up, thumbs down when you're dealing with this. So we had one equation: power equals torque times angular velocity. So angular velocity is how many radians per second the wheel's turning. Your
Mhm.
power is fixed. That's just fixed by the mousetrap. You've got a X amount of power you're going to get out of that period. Now you can tweak it to try to make a certain amount of energy come out slower, and that
Mhm.
gives you more energy per unit time. And that's what gears do. But you're still fixed with your power. So your power has torque times angular speed or is a constant.
Mhm.
And you need enough torque to carry a heavy battery, and that fights the angular speed, because the faster the angular speed, the lower the torque. So you've got to do that, and really what you're wanting to do, probably the single most important thing, is focus on it keeping its grip, which is why they wanted to make it heavy, but probably are going way too far overboard. So you want to keep it
Mhm.
somewhat heavy, and then you want to also make sure that you can spread the power of the mousetrap doing this over as many revolutions as possible.
Okay. Okay, thank you.
You're
Yeah,
welcome. I hope that helps. And
it does. It does.
But
I was just, yeah. I
it's
was
real
just hoping
easy to
like-
want to do a lot of calculations with that. And in principle, there are fundamental calculations you can do, but setting certain standards like that and just thinking thumbs up, thumbs down, that's probably all you need for this. And then the experimental results to tell the people to shut up and stop treating me like a girl.
Okay.
Because that happens in groups and it sucks. I feel bad for people. And I probably do it too, and I never try to, because I know there's a lot of women smarter than me. But yeah, that's going to happen in your group. But if you have the results, then they got to shut up or they're stupid.
Okay.
Okay.
Yeah, I was saying that they're older than me, and it is males, and yeah, so
That happens a lot in sciences and engineering. So wade through it, survive, and you'll be the kick butt engineer when you're done. Okay.
thank you. Okay, thank you so much.
You're welcome. See you, Victoria. Have a good day.
Thank you too.
I don't think Hassan's really here. Hassan, did you have a question, sir?
He's in my next class, which starts now, so
Okay,
yeah,
so he's not
fine.
there. All right, see you.
Bye.